Myanmar earthquake, the supershear velocity explained. Imagine the ground beneath you suddenly tearing open at speeds faster than a jet plane. This wasn't a scene from a disaster movie, but the reality of Myanmar's catastrophic earthquake in March. On March 28, a 7.8 magnitude earthquake struck Myanmar, leaving over 5,000 people dead and causing extensive damage that reached neighboring countries. But here's where it gets controversial. The southern part of this earthquake's rupture moved at an astonishing speed, known as supershear velocity. This phenomenon, where the rupture speed exceeds the velocity of shear waves, likely amplified the earthquake's destructive power. But what exactly does this mean, and why should you care? Let's dive in. In a study published on July 10 in the Seismic record, seismologists confirmed that the southern portion of the earthquake's rupture zipped along at speeds ranging from 3.1 to 3.7 miles per second, 5 to 6 kilometers per second. To put that into perspective, that's faster than the speed of sound. This supershear velocity is a rare and particularly dangerous occurrence in earthquakes. But why is that? Let's break it down. When an earthquake hits, the first waves to arrive are P waves, or primary waves. These waves travel quickly through the earth, compressing and expanding the material they pass through, but they don't cause much damage. Following the P waves are the S waves, or secondary waves, which move more slowly but cause significant destruction due to their side-to-side motion. When a fault ruptures at supershear velocity, it means the break along the fault is moving faster than the S waves themselves. In most earthquakes, rupture velocities typically range from 50 to 85% of the S wave speed. But in Myanmar's case, the rupture outpaced the S waves, leading to a more devastating impact. The earthquake occurred along the Sagaing Fault, a strike-slip fault that runs north-south through Myanmar. Strike-slip faults are where two tectonic plates slide horizontally past each other. In March, this fault put on a dramatic show, with footage capturing the ground suddenly lurching forward. The rupture extended about 298.3 miles, 480 kilometers, along the fault, which is extraordinarily long for a strike-slip earthquake of this magnitude. Seismologists, using seismic and satellite data, found that the rupture caused a significant slip of up to 7 meters, 23 feet, extending about 85 kilometers, 52.8 miles, north of the epicenter near Mandalay. To the south, the slip was more patchy, ranging from 1 to 6 meters, 3.3 to 19.7 feet, along approximately 395 kilometers, 245.4 miles, with about 2 meters, 6.6 feet, of slip near the capital, Nay Pyi Tav. A seismic station near Nay Pyi Tav recorded ground motion data that provided clear evidence of the supershear rupture. Thorn Lay, a seismologist from UC Santa Cruz, noted that the time between the arrival of the weak, compressing P wave and the large shear offset of the fault was unusually clear and convincing. This offset is the ground displacement that occurs along a fault during an earthquake. Lay and his team suggest that the supershear velocity, combined with the rupture's strong directivity, where S waves pile up in the direction of the fault line as the rupture spreads, might have contributed to the widespread damage. The Sagaing Fault is no stranger to large earthquakes, but the March event involved a segment of the fault between Mandalay and Nay Pyi Tav that had been quiet since 1912. Lay pointed out that a better understanding of fault segmentation and geometry is needed to predict future events. But here's the part most people miss. While we can't predict earthquakes with precision, earthquake early warning (EW) systems can provide crucial last-minute alerts. These systems send out electronic alerts that travel faster than seismic waves, giving people precious seconds to prepare. And this is the part most people miss. The smartphone-based Android Earthquake Alerts (AEA) system has proven to be as efficient as traditional seismic networks, offering hope for regions without the necessary infrastructure. So, what do you think? Could better technology and understanding of supershear velocities help us mitigate the damage from future earthquakes? Or is this just another example of nature's unpredictable fury? Share your thoughts in the comments below, and let's discuss. First ever visual evidence of curved fault slip captured on CCTV during Myanmar earthquake. **** earthquake caught on camera. And it's not what you think. **** Dramatic CCTV footage of a major earthquake in Myanmar has captivated scientists and the public alike. The video, initially shared on YouTube, showed the ground visibly shifting during the quake. But here's where it gets interesting. A closer look revealed something truly groundbreaking. Geophysicist Jesse Kuss, along with his colleague Yoshihiro Koneko at Kyoto University, noticed something extraordinary on repeated viewings. The ground wasn't just moving, it was curving star. This seemingly subtle detail is a monumental discovery for earthquake science. The researchers, after meticulous analysis, concluded that the video provides the first direct visual evidence of curved fault slip star. Think of it like this: imagine two bricks sliding past each other. Typically, we envision them moving in a straight line. But what if they moved along a curved path? That's what this video appears to show. Now, geologists have long observed curved slicken lines, essentially scrape marks left on rocks after an earthquake. These slicken lines hinted at the possibility of curved fault slip. But until now, there was no visual confirmation. This video, captured along Myanmar's Sagaing Fault during a magnitude 7.7 earthquake on March 28, provides that missing piece of the puzzle. The camera, positioned about 20 meters east of the fault and 120 kilometers from the earthquake's hypocenter, the point of origin underground, captured a truly astonishing sequence, the ground visibly sliding northward along a curved path. Kuss, recalling his initial reaction, described the footage as chilling. He explained, "It shows something that I think every earthquake scientist has been desperate to see. And this is the part most people miss: the implications of this curved slip are significant." Kuss's previous research focused on curved slicken lines from other earthquakes, like the 2016 Kaikoura earthquake in New Zealand. He was already investigating how these curved lines could help us understand how faults rupture. The Myanmar video provided a real-time example to test these theories. To analyze the video objectively, Kuss and Koneko used a technique called pixel cross-correlation. This allowed them to track the movement of objects in the video frame by frame, measuring the speed and direction of the fault's motion. Their findings? The fault slipped 2.5 meters in about 1.3 seconds, reaching a peak velocity of 3.2 meters per second. This pulse-like movement confirms previous inferences from seismic data of other earthquakes. Furthermore, the movement was primarily strike-slip, horizontal, with a brief dip-slip, vertical, component. But here's where it gets controversial: why does the fault slip curve? The researchers found that the slip curves rapidly as it accelerates, then becomes linear as it slows down. This pattern aligns with existing theories suggesting that lower stresses near the Earth's surface might influence the curvature. Essentially, the dynamic stresses during the rupture initially push the fault off its expected straight path, before it corrects itself. Even more intriguing, the direction of the curvature appears to depend on the direction the rupture travels. In the Myanmar earthquake, the rupture moved north to south, which correlates with the observed curvature. This suggests that slicken lines can act as a record of past earthquake dynamics, offering valuable insights into future seismic risks. Could this mean we can better predict earthquake behavior? This discovery opens up exciting new avenues for research. By creating more accurate dynamic models of fault ruptures, scientists can potentially improve earthquake hazard assessments. What do you think? Do you agree that this video is as groundbreaking as it seems? Share your thoughts in the comments below. Witness Earth's violent convulsions, the Myanmar earthquake's savage truth. Imagine witnessing the Earth's surface suddenly shifting sideways during an earthquake, something most of us have only read about or seen in simulations. But here's where it gets controversial: a recent video from Myanmar's devastating magnitude 7.7 quake offers the very first direct visual glimpse of this powerful natural process in action. This groundbreaking footage provides fresh insights into how tectonic plates move and rupture at their boundaries. During this catastrophic event on March 28, a CCTV camera captured a remarkable moment. The Earth's crust along a fault line suddenly lurched, revealing the violent, abrupt nature of plate boundary movements. Tectonic plate boundaries are zones where large chunks of Earth's crust slide past each other, not smoothly, but through sudden, forceful ruptures. The video shows the surface jerking sideways, almost like a giant conveyor belt flicked on for a split second as the fault slips. What we're observing is the propagation of a major earthquake rupture, the primary way that the Earth's surface accommodates the movement of tectonic plates. These shear fractures can travel at several kilometers per second, making them notoriously difficult to observe directly. Such rare events, which occur roughly once every few centuries, have sculpted our planet's surface over millions of years, creating features like New Zealand's Alpine Fault and the Southern Alps. Until now, seismologists have primarily relied on seismic data collected from distant instruments to infer how faults ruptured during large earthquakes. This new footage, however, offers a rare, real-time glimpse into the process, shedding light on how seismic energy radiates and causes the ground to shake. In our recent study, we analyzed this video frame by frame using a technique called pixel cross-correlation. This method allowed us to measure the fault's slip, how far it moved sideways, finding it to be approximately 2.5 meters over just 1.3 seconds, with the maximum slip speed reaching 3.2 meters per second. Such a significant lateral displacement is typical of strike-slip faults, which move the land horizontally, unlike faults that cause vertical uplift. But what truly stands out is the short duration of this slip. This is a major discovery because measuring the exact timing of when a fault begins and stops slipping is usually challenging with seismic signals, which tend to become smeared as they travel through Earth. The brief, pulse-like nature of this rupture suggests a concentrated burst of slip that propagates along the fault like a ripple spreading across a rug when flicked, an insight that could revolutionize how we understand earthquake dynamics. Understanding these details is crucial for improving our predictions of ground shaking during future large earthquakes. The more precisely we can observe how faults rupture, the better we can prepare for their impacts. Our analysis also uncovered a subtle but important detail about the fault's movement. Instead of slipping in a straight line, the fault's slip path was curved. This curvature aligns with patterns observed in geological scratch marks called slicken lines on fault outcrops, rock surfaces that record the direction of slip. Our findings confirm that these slicken lines are indeed curved, matching the curvature seen in the CCTV footage. This provides strong evidence that geological features on the surface accurately reflect the actual slip behavior during earthquakes. In previous research, we used computer models to demonstrate that curved slicken lines can naturally form when an earthquake propagates in a specific direction. The Myanmar rupture traveled from north to south, consistent with the model's predictions. This alignment boosts our confidence in using geological evidence, like slicken lines, to determine the direction of past earthquakes, such as the 1717 rupture along New Zealand's Alpine Fault. This first-ever glimpse of a fault in motion highlights the incredible potential of video technology in seismology. With more strategic deployment of cameras and recording equipment, future earthquakes could be documented in similar detail, offering unprecedented insights into the mechanics of fault rupture. Such advancements could fundamentally change our understanding of earthquake physics, and perhaps even improve our ability to predict and prepare for these powerful natural events. So, do you think visual evidence like this will become a standard tool in earthquake science? Or are there limitations that still need to be addressed? Share your thoughts and opinions below. This is a topic that definitely sparks debate.